Hi everyone, I'm Beliz. Today we are going to look at advanced location and routing models. Until now, we only talk about placing one new facility, but in real world, big companies open multiple factories and route of hundreds of trucks. Today we will learn how they do it. Let's get started. When we look at the advanced system, the question gets much bigger. We don't just ask where do we put this building. We have to decide how many new facilities do we actually need, where is the exact best location for all of them, how big should they be, what should be their capacity, which warehouse will serve which customer, and can a customer get deliveries from more than one place. It's like a giant puzzle. To solve this giant puzzle, we break our problems into three main categories: location problem, allocation problem, and routing problems. In location problems, putting multiple new buildings on the map. Location problems, deciding how products flow through the network. We will look at the two-stage transportation model for this. And lastly, routing problems, planning the exact driving paths for delivery trucks, like traveling salesman problem or vehicle routing problem. Let's start with location. This is called in-facility location problem. Imagine you have distribution network with some existing facility. We call them N. Now you want to add several new facilities. We call them N. To find the total cost, we must calculate two things: the distance from the new building to old building, and the distance between the new buildings themselves. They all interact with each other. Let's make this easy to understand with a coffee company example. Bean and Brew has four existing cafes and one central roastery. Our goal is to find bus map coordinates for W1 and W2 so the company spends at least amount of money to delivering coffee beans. We know how many trips the trucks make every day. Um, and we are going to use rectilinear distance, which means driving on city streets. To find the best location, we use linear programming. Let's look at step one. Normally, we measure distance using absolute values because distance can never be negative. But computer programs like GAMS and Window, absolute values are not working. So we use a clever trick called linearization. We split every single distance into two parts: positive variables like xp and negative variables like xn. Now let's look at the step two, objective function. It's actually very simple. We are just taking the number of daily trips and multiplying it by the distance for every single route. For example, there are 7 trips between Cafe A and New Cafe W1. So we multiply the distance variables by 7. Our goal is to minimize value z, which means keeping our total driving cost as low as possible. Of course, a math model needs rules. In step 3, we set up our constraints. These equations simply connect the unknown coordinates of our new cafes to the exact known coordinates of the old cafes. It basically tells the computer how our map works so it doesn't break the rule. Once we have our objective and our rules, we feed this entire block of math into our solver software. The computer give us our final perfect answer. This the optimal spot for the first cafe at in W1 is at coordinate 10 to 25, which means it should be placed exactly where cafe A is in. The best spot for the second cafe W2 is at 15 to 25, which right on top of the cafe C. If you build them there, our absolute lowest total cost is exactly 370. Okay. Now, what if we use Euclidean distance? That is straight line distance, like flying a drone. If we use bigger version of this field algorithm we learned before, but there's a math danger here. If computer places a new facility exactly on top of an old facility, the distance becomes zero. In our formula, that means dividing by zero, which breaks the math rule. To fix this, we just add a tiny number called epsilon to the bottom of the fraction in here. This stops the error, and the computer can safely loop the math until it finds the perfect location. Finally, let's look at the allocation models. This is a two-stage transportation model. Look at this diagram. It's a real supply chain. We have our sources, like factories making products. We have our plants, like warehouses storing the product. And lastly, our customers who wants the product. We are shipping into two steps. Stage one is shipping from the source to the plant, and stage two is shipping from the plant to customer. We want to find the cheapest way to flow goods through this whole system. To solve this, our objective function minimizes cost of both shipping stages added together. We have 5 simple rules, constraints for the system. First one is capacity. You cannot ship more than the factory or warehouse can hold. Second one is demand. Make sure the customer get exactly what they order. Third one is material balance. This is the most important rule. Every single unit of product that goes into a warehouse must come out of the warehouse in equals out. When you put all these rules together, the system optimizes your shipping and makes sure everyone get their own coffee on time and on budget. Now for the final step, routing. How do our trucks actually drive there? This brings us to a famous traveling salesman problem, or TSP. Imagine a salesman. He must visit a set of cities exactly one time and then return to his starting point of city. Our job is to find the exact order of cities, the tour actually, that gives the shortest traveling distance. You can see on this map, we are connecting the dots to make one big perfect loop. This gives to give this to a computer, we usually use a variable called xij. If salesman drives directly from city I to city J, it will become equals to 1. If not, it will be equals to 0. We need rules so the computer doesn't cheat. So first one, leave once. You can only drive out of the city one time, and you can also enter the city also one time. And lastly, subtour elimination. This rule is super important. It forces the route to be one giant connected loop instead of two small separate circles. Now let's look at the routing. Big companies don't just have one salesman. They have a big giant fleet of trucks. This is called vehicle routing problem. Here, many identical vehicles start at a single depot. must return there. Every truck has limited space inside, which we call capacity. And every customer wants a specific amount of goods, which is called demand. We have to find the best route for entire fleet. The math is similar, just bigger. Our objective is to minimize total distance for all vehicles. Um, the new rule here is the vehicle capacity constraint. The total demand of all customers on a truck route cannot be bigger than the truck's maximum capacity. You can put 100 boxes in a truck that only holds 50. And finally, we still use our MTS rule to make sure every truck makes proper um, loop. And that is all for today. Thank you for watching.